Alright, this lesson is about approximating the area underneath the curve. Naturally, if the curve is something complex, then we really need this idea of estimating or approximating. But if the curve is something really simple, then we might be able to find it exactly. So the first thing I'm going to do is to begin with a very simple example where you can find the area exactly. So this is just the area underneath the curve. So I'm going to think about a pretty simple scenario here. And I'm going to pull from an application because those are oftentimes the easiest to understand. So we can look at a time versus velocity graph, right? This kind of thing here. So you can imagine that we're traveling at a constant velocity, and I'm going to keep this really nice and simple. So we could say something like 60 miles an hour, so something really simple. And then we could say, suppose we do this for a certain amount of time. So for example, 2 hours. And then I'm going to enclose this figure here. And the question we're going to ask ourselves is, finding the area enclosed by this, what is the meaning of that? So just calculating this area. So this has some really important applications, or definitely some important meaning in calculus. So when we calculate the area of this, it's going to be very simple because it happens to be a rectangle. So the area here we can get by multiplying two numbers, right? Just by looking at the height of the rectangle, that will be the 60. So I'm going to write this as 60 miles per hour. So we take this number and multiply by the width of the rectangle, and this would be 2 hours. So what we get out of this is, you could see when you multiply these two numbers, the time unit is gone, and you end up with displacement. 2 times 60, right, is 120 miles. So this tells us, in some sense, how far we traveled, right? And it makes sense. If you travel 60 miles an hour for 2 hours, that's exactly your displacement there, 120 miles. So the big connection to make here is, this seems to be a calculation that might not have any inherent meaning, but it gives us something very important in the application context. So what we'll be doing the rest of the time is talking about estimating the area, because oftentimes the curve that we have here is not a constant function, it's something that is more complex. So number one thing we're going to do is to talk about some notation first, and then we can get to this idea of estimating area. So the big notation we're going to see a lot of in this lesson is the sigma notation. So we borrow this from the Greeks. Okay, and this simply means to add up, so we're going to sum some things up. So the standard notation here, we might see something like this, I going from 1 to 5 of I. So I here is the index, and I begins at 1 and then it stops at 5. And so what we're doing here is we're adding up those numbers, just the i's. So the way to interpret this is we're going to start at 1 and stop at 5, so you can write down the numbers. 1 to 5, and then again the sigma here means to add. So we just take these and we add them up. Okay, so this is a fairly simple exercise. So we get 12, it looks like 15. So the big takeaway from this is, rather than writing out a long list of numbers, right, adding these up, this is the compact way of expressing it, right? So this is just a shorthand for this notation here. So you can add up many other things. So we could do, for example, I going from 1 to 4, and you don't have to add up I, you could add, for example, its squares. So you could add up those there. So this again would mean begin your work at 1 and stop at 4, but you're adding up the squares. So it would be 1 squared plus 2 squared, all the way down to 4 squared. Okay, so that's what we would do. So this here, 16 and 9, right, would give us 25, and we're going to add 5, so it looks like 30 here. So it's important here, before we talk about the area under the curve, just to be fluent in this kind of notation, right? It just indicates a compact way of expressing a long list of sums. Naturally, if you're only adding 4 or 5 things, there's little benefit to expressing it this way, but if you're adding many things, then you really want to get comfortable with this notation here. Alright, so the rest of the time we're going to talk about a fundamental problem of estimating the area under the curve. So let's take a look at a problem here. And so here it is. So what we're going to do here is to see, let's estimate or approximate the area underneath this function, right? So this is y equals 4 minus x squared. Nice parabola. And we're going to estimate the area underneath it beginning at 0 and then stopping at 1. And it's usually given here that when we're finding the area under the curve, it's implied that we're talking above the x-axis at the same time. And so to estimate the area, because the shape is irregular, we're going to use a very easy shape, a very convenient geometric shape, which would be a rectangle in this case. So first thing we'll try to do is just to get a handle on what the graph looks like, because it's always good to have an image of what's happening. So here we have the function y equals 4 minus x squared, and we're going to start at 0 and stop at 1. So this orange portion here is what we're trying to estimate. So the problem here with finding this exactly is it is not a convenient geometric shape. So we're going to zoom in on this area here and then break down this region into rectangles, and we're going to try to approximate it. Okay, so the basic idea is we're going to do something like this, right? If you're going to use 4 rectangles, then we're going to look at this orange little area here, and rather than trying to compute this exactly, we're going to break up the region into 4 parts. And what you'll notice is that we sketch these 4 rectangles. So we're going to divide 0 to 1 into 4 parts. And then also we're going to have these little heights touch the curve, right, at the upper right hand corner, and then this way we can calculate the heights. So I'm going to put this on top right here, and then we'll make a couple of notes here. So the function in the problem is this 4 minus x squared, right? So if you wanted to look in detail, how do you find the area of this first rectangle? The key here is going from 0 to 1, this will have a width of 1. And if you count 4 rectangles, then that means the width of each rectangle will be this entire length divided by 4. So if you think about, I'll just focus in on this first one, right? So the width of this rectangle will be 1/4. Right, so we get 1/4 there. But then the height of this, what you would have to do is you look at the upper right hand corner, and I'll try to highlight this in color so you can see it. So if the width is 1/4, then this means we would have to take the number 1/4 or 0.25 and actually insert it into the function, and you'll notice that it touches the curve at the upper right hand corner. So if you want to get the height of the first rectangle, you would have to insert 1/4 into this function. So we'll make a note of that here. So the height here would be f evaluated at 1/4. So this here all comes from the diagram. And then as you proceed in this, you could tell that the width is not going to change for these rectangles, but the height is. And so the height is going to depend on the number that you plug into the function, and then that is going to give you the height of that rectangle. So this thing that we're seeing here in front of us, we could call it a right sum, or we might call it a lower sum, because all of this white space that we see here indicates that we're missing out a little bit on the orange area. Right? So this here is going to give us overall an underestimate on the area. So I'm going to put this one back up and illustrate mathematically what it is that we're calculating. So this is the important part. It's a little busy on the notation, but it's important to understand what we have in front of us. So if you want to calculate the area of all 4 of these rectangles, then that means you're going to be using a height and a width 4 times. So when you look at this expression here, the very first one that we see here, and I'll highlight this, right? So you can see the height, f of 1/4, and then times the width of 1/4. And this is exactly the data that we have here, the width and the height. So if we take those 2 numbers and we multiply them, that's going to give us the area of the first rectangle. And then you can see this process is going to change for the other 3. The width is the same, but then the height is going to be calculated at a different value on the x-axis. So if you look at the way this is written out, this is the compact way of expressing it, right? So you can see I is running from 1 to 4, and so you'll have 1/4 as your first input, and then you'll stop when you get 4 over 4, so f of 1, right, will be your last one there. And so then, if you wish, you can pull out a 1/4 and then just calculate all of these. Remember that the f is coming exactly from this function, because all of the heights are touching the function at that point. So then when you calculate the area, it appears we get about 3.5, 3.53125. And that's a pretty reasonable number if you think about the width here is 1 and the height here is 4. And we're missing out a little bit on the upper right hand corner, so this value here should be less than 4. Alright, so once we understand that, then basically the idea is very similar, because this number here would be an underestimate on the area. So what we will typically do is to also do the same thing on the other side of business, and that is to get an overestimate on the area. So I'm going to show you a picture here that is a little bit different. That's this one here. And so what we'll notice is a calculation here will be very, very similar. Okay, so it is good to compare the previous picture with our new one. So this was our old calculation here, where you can see that if you calculate the area of the blue, it's not going to quite give you the area underneath the curve. But if you calculate the area here in blue, it actually gives you too much. So this here would be an overestimate or an upper sum. This one is our lower sum. So most of the work here is identical. The only thing you'll notice here is there's a shift in the calculation. So if you're using 4 rectangles, you're still going to have a width of 1/4 for each one of these. So you can see that number show up 4 times. But then the thing you'll notice, for example, you might focus on the last rectangle, if you will. And then if you ask yourself, what number do you have to plug in to get the height of that rectangle? And this time it's on the left. So if you insert 0.75 into the function, that's going to allow this rectangle to hit in the upper left-hand corner, right? This value here. And then you can see that's going to give you the height of this rectangle. So the last output that you see here is f of 0.75. And that is different than our previous calculation. It's because the first rectangle here uses a height when you insert 0. So otherwise, in terms of structure, this is identical, but the calculation is slightly different. And it should make sense that the last time we did this, we got about 3.5, but now because we have a larger computation here, an overestimate, this number is slightly bigger, right, the 3.78125. So we could really say that the previous the two calculations that we see, neither one of them is correct for the area underneath this curve from 0 to 1, but both of them are fairly close. So we can say for certain that the actual area has to be in between those two numbers. So this is the nice thing that we can say with confidence, and one of the values you can still see here. So the upper sum here was 3.78125. This was our lower. So if you go back to the diagram, that would be the original one right here, okay? We don't know this exact area between 0 and 1 and underneath the parabola, but we can say with certainty it has to be in between these two numbers, because we intentionally underestimated here and intentionally overestimated there. So I think the extension here is pretty natural, right? What you would expect, what you would have to really do here. So if you go back and you look at this example, the first one that we did, this was somewhat unsatisfactory to calculate this. So what we would do to improve this is to increase the number of rectangles. So here it's rather crude that we're only using 4, and we have a lot of this white space, right, that is missing out on this area here. So you can see just by a quick diagram, if you have the exact same curve and you double the number of rectangles, suddenly there's much less white space here. So you would expect the lower sum here that we get here is actually going to increase a little bit because you're going to have more of this area here filling in. So this is the basic idea in calculus, is to use a greater number of rectangles. So I'm going to put this back up here so we can look at that statement. So this is what we did early on, right? So if you increase the number of rectangles, you're going to expect your lower sum is going to increase and grow. And if you increase the number of rectangles, your upper sum is going to have less overhang, right? So this number here is going to start to drop. So the key is, if these numbers are close to one another, then you're getting a better and better accurate of the true area underneath the curve. So I want to give you just a sense of what this looks like, because this one here, right, the standard notation that we would use in calculus, this is what we got when we used 4 rectangles, right? Both the upper sum and the lower sum. So if you repeat this process for even just a fairly small number, but something bigger than 4, let's go to 10, you see quite a big difference, right, in what is happening here. So this would be the same calculation if we repeated the process, if we more than doubled the number of rectangles. So if you use 10 rectangles, you can tell that 3.53 grows, right, to 3.615, and your upper sum here, 3.78, is going to drop by quite a bit to 3.715. And the key here is we would trust this calculation more, or this one would be better, because there's less space between these two numbers. So now we can say, after doing this calculation with 10 rectangles, the true area underneath the curve, even though we don't know what it is, has to be in between these two numbers. And you can see that these numbers are a tenth away, right? They're pretty close to one another. So as we move forward in calculus, what we're going to do is to use larger and larger numbers, and you can tell that this is definitely fit for a computer, right? So we can import the basic formula into a computer, and then we can watch what is going to happen here with this interval here. So ultimately, the goal here, if you want to calculate the exact area underneath the curve, again, we're talking about this picture here, where the shape of the object is irregular. The key here is n has to be infinitely large, right? So that's the idea where we have to bring the idea of a limit into this problem to find the exact area under the curve.